Okay, next we're going to show a very useful result that doesn't require much condition. So the requirement that we have is only, or the condition we have is only that every EK here is a measurable. So suppose we have a sequence of EKs that are measurable, then we will have this result. The measure of the lower limit is less than or equal to the lower limit of the measure. Okay, so let's see how to prove this. Okay, let's first look at the left-hand side. Recall that the lower limit of the sets is defined by this, right? So basically means that there exists some k such that if x is in the lower limit of ek, then that means x for some k, the x will be in ek plus 1, and so on and so forth. So that's the definition we gave in the first lecture. So recall that this part, if I define to be the bk, okay, so for every given k, my bk is just taking the intersection of the ej's for j greater than or equal to k, then you can see that this bj is actually increasing, right? So bj you can see the b1 belongs to b2 belongs to b3. In other words, this bk is increasing or non-decreasing in k. And the reason of this is because for larger k, we will be taking intersection of fewer sets, right? If the k is larger, then we're taking intersection of fewer sets, so that's why the bk is potentially larger. So the bk is increasing, and then we can also know that this is just according to the definition of bk, this is just the union of the bk, and this is just the limit of bk, right? So that's why to prove the claim of this corollary, what we need to do is to look at the left-hand side, ek, and as we just showed, this is just the measure of the limit of bk because bk is monotone. Okay, and by the theorem we just showed, this since the bk is increasing, so the measure of the limit is equal to the limit of the measure, right? For increasing case sequence, we have this. And now you can see that the bk, remember that the bk is defined in this way. Okay, so bk is the intersection of that. So that means bk must be contained in ek, because it's the intersection of ek plus 1, ek plus 2, so on and so forth. So it must be contained in ek. And if this is contained in ek, this actually means that the measure of bk is less than or equal to the measure of ek. Okay, so if you're on the left, if the limit exists, as we showed, the limit of this mu bk is just this quantity here, right? The limit of the measure of bk is just this, which is just equal to this. So the limit exists, but if your bk, if this quantity is always less than or equal to, as we showed, this is always less than or equal to this, then that means the limit must be less than or equal to the lower limit of the mu ek. Okay, so the mu ek itself may not be convergent, but it must have a lower limit, but the lower limit must be bigger than or equal to the lower limit of mu of bk. But since mu of bk has a limit, so the lower limit is just the limit itself. That's why we have this, and that finishes the proof. So let's. I want to make two remarks here. The first one is that we see this inequality here, and in general we do not have the equality. Okay, so this is the thing that you need to be careful when you apply this this corollary. The reason for this is because, say, we have. I'll give you a counter example here. Suppose we have ek to be the interval 0 to 1/2 for k equals to, so this is a subset of our just closed interval over R. And for k, for example, for k is odd. And I will set ek to be 1/2. I can put it closed 1/2 to 1 as well. It doesn't really affect our conclusion. So for k is even, I will set to this. Okay, so now you can see I have this this rule line 0, 1, 1/2. So that means if for E1, E3, E5, I'll take it will be just this set, this interval. If it's E2, E4, E6, it will be this set. Okay, and now you can see what are the lower limit of the sets. So the lower limit of the sets, according to our definition, is just this. Right? And we know that this means that if point x is in this lower limit of ek, then it must be in all the ek starting from some k. Right? But apparently, my sets are switching. Right? So one for all number k's, this will be this. For even numbers, it will be this. So they will not overlap, and that's why this will be just an empty set. And that implies that the lower limit has a measure 0. Okay, and on the other hand, let's look at the ek itself. So all of the ek's we have seen so far, they all have the measure 1/2 because they are these intervals. Right, so the measure of them are 1/2. So the mu of ek is equal to 1/2 for all the k's, and that's why the lower limit, actually the limit even exists, will be just 1/2. And that's why go back to this corollary, we can see that this side could take 0 value and this could take the 1/2. So in general, we do not have equality. We only have less than inequality, less than or equal to. Okay, so that's the first remark I want to make. Second remark is that if you are working on upper limit instead of lower limit, we can have something similar. However, we must have a boundedness on one side. So if all those ek's are bounded, or they have finite measure, okay, easy way to show that is to have this is that all the ek's are contained in some set E, and this set E has a finite measure, then we actually can have the lim sup, or let me write it another way. Mu of the lim sup, the upper limit, will be bigger than or equal to the upper limit of the measure. Okay, and the reason is very easy. We can just show this by looking at the left-hand side. Say, I can have the mu of E. So since we can say that the E is we can look at the E minus EK. Okay, and notice that if we take the lim sup of EK, then the lim sup of EK as we know, this is just equal to this, right? So if I take a complement on both sides, I'll have this, right? And then this right-hand side, by using the De Morgan's law, is equal to this. I just need to switch the intersection and the union. I'll get this. And also, I need to put complement on each of those sets. So this on the right-hand side is just the lim inf. Okay, so it's taking the lim inf of this. So on the right-hand side, I can apply the corollary we just had. So it's mu of lim inf, the lower limit of EKC, and that's just less than equal to the lim inf of mu of EKC, right? So this left-hand side, as we showed, is just the mu of the lim sup of EKC. Okay, so we can write this. Let's say that the E is the universe, right? It's the whole set, and we can just say that the complement of that is just mu of E intersect with this lim sup. And this is just equal to the mu of E minus the mu of the lim sup of EK. Okay. Oh, by universe I mean that the EK is the whole thing. Just let's say this is the whole E. Okay, because we're only concerned about these EKs, which are all included in this E. So this is maybe E1, maybe E1, maybe this E2, but they're all in E. So we're just concerned about this E itself. I don't care about what happens outside of E. Okay, so that's why we have this. And on the other side, we have shown that this is equal to the lim inf of mu E minus mu of EK, right? So now see that this lim inf is just equal to the mu of E minus plus the lim inf of the negative mu EK, and that it just becomes positive, or just minus lim sup of mu EK. Okay, this is because the lim sup of negative, say xk is a sequence, this is just equal to negative of lim inf of xk. Right, you know this. So that's why we actually have, well, we can use the inf here and the sup here. So the upper limit of the negative xk is equal to the negative of the lower limit of xk. Okay, so that's why we can get this. So now we have showed that this quantity here is less than equal to this quantity here. Sorry, this quantity here. And you can see that the mu e is on both sides and it's finite. So we can cancel this. And that's how we prove that this quantity is actually bigger than this quantity. And that is the claim we're trying to make. Okay. See. Yeah, so this is less than this because the negative of this is bigger than negative of this. So this is less than this. Okay? And that's how we show this is less than this. Okay, so that's the second remark I want to make. So you can apply this to the upper limit, but you just need to make sure that these EKs are have finite measure starting some in some set E. Okay, so otherwise it may not work. And the reason is that in the proof we may not have this. We may not be able to cancel this. Okay, so next theorem. Next theorem I'm going to prove is suppose we have a open set G. Okay, on this Rn, and we have E contained in G. Okay, and the E can be any set, doesn't have to be measurable. So what we're trying to show here is that if we define the EK to be the points in E, at the same time the distance between X and the G complement is bigger than 1 over K. This is my EK. Okay, for any integer K, for any natural number K, then I will have the limit of the outer measure of EK. The reason is we don't really know if the EK is measurable, since the E is not necessarily measurable. Okay, so the E may not be a measurable set. So that's why I only have the outer measure here, and we can show that this is true. Okay, so what this says is, suppose we have this E here, and we have and this E is contained in some open set. Let me say that this is the open set G. It's contained in G. And I will define a subset of E, as we see that this is only a subset of E. And this EK is a subset of E such that its distance to K complement, to everything outside of this, is bigger than 1 over K. Okay, so the EK will be just a subset of E. And apparently the EK is increasing. The reason is, as you can see, if I increase the K, this number is actually getting smaller. And that means I can include more points which are closer to GC. Right? The original points for K, for fixed K, the points in EK will be also in the set EK plus 1, because the 1 over K plus 1 will be even smaller number, and their distance will be definitely bigger. If the distance between X and GC is bigger than 1 over K, then it must be bigger than 1 over K plus 1. Okay, so that's why the set EK is actually a sequence of increasing sets. Okay? And because of this, it is obvious that since EK is in E, so we know that the outer measure of EK is also less than or equal to the outer measure of E. And we know that EK is increasing on the left-hand side. When we take K to infinity, the limit will exist because it's bounded above by this mu star of E. Okay. Next, let's see. What if, since my EK is contained in E and the EK is increasing, what if we take the union of EK? Can we get this E? As we can see earlier, when K gradually increases, my set EK is also gradually growing, right? And then the question is if they can grow to the entire E. And the answer is yes. The reason is for any X in E, and then we know that E is a subset of G, so that means X is also in G. And because X is in G and G is open, we know that there exists some delta such that the Bx delta is completely inside G. Okay, so that means any point in E will have some positive distance from G complement. Right? For any point in E, I know that there will be some ball centered at this point X with some positive radius such that this ball is completely inside G. And that means it still does not overlap with the G complement. And that means the distance between this point X and the G complement will be bigger than delta. Right? The distance of X and GC will be bigger than delta. Well, if it's bigger in delta, then for K large enough, then 1 over K will be smaller than delta. And that means X will be in the will be in the EK. So X will be inside the EK if K is sufficient large such that delta is bigger than 1 over K. Right? So, and what we show so far is that any point in E will be in EK for K large enough. And that means if I take the union of those EKs, I will get the E, right? Because every point in E will be in some of the EKs. So I know that the E will be just the union of the EKs. Okay. Now, let's say that since what I have shown so far is that the EK is contained in E, and the E is also the union of the EKs. And I know the limit of EK is bounded about by the mu star of E. So what I want to show is that the limit of this is actually equal to this. Okay, so I actually want to show that taking the limit of this is equal to this, not just less than equal to. Okay, to this end, let's show that define my dk to be ek minus 1. So we know that the sets are increasing. So that's dk is just taking the difference between the two concatenate sets. So if I define my ek to be this for k greater than or equal to 1, then, so let's say the E0 is just 0. Okay, E0 is just 0. And then I can define my dk for all the k greater than or equal to 1. And in this case, I will see that the E is the union of the EKs, but it's also the union of the DKs. Okay, so now let's see the what if I just look at the union of the first 2k of the EKs. So let's say the EK, I know that this is greater than or equal to any of those EKs. So let's say I'm looking at the E, say 2k. Okay, And the reason I'm doing this is because this will be equal to the mu star of the union of k from 1, use j here, j from 1 to k of this dj. Okay, and now I can see that this d, I can separate this to 2. The one is only on the even numbers, and the other one is only on the odd numbers. So let's say it's from 1 to k. It should be 2k here. It's j is from 1 to k for the d2j, and the other one could be the j from 1 to k d2j minus 1. Okay, so I separate the even indices and the odd indices. Okay, so what I know about this is it must be bigger than equal to the one of them. Let's say first one of them should be bigger than equal to this. Okay, so I only use this set here, so I don't care about this. But this is the union of the two, so it must be, according to the definition, according to the property of the outer measures, it must be bigger than equal to the outer measure of just a subset of that. Okay, so now I'm going to claim that this is equal to the sum of this d2j for j from 1 to k. Well, the reason here is I need to make a claim. Say I have two sets, A and B. Say A and B, and their distance. So if the A and B such that the distance between them is positive, then I'll claim that the mu star, the outer measure, actually has this additivity, which means this is equal to this plus this. Okay, if their distance is not greater than 0, it's equal to 0, then we cannot really make this claim. But if it's bigger than 0, we can make. And the reason is, first of all, I will first show the proof of this claim. So for the A and B, the union of A and B, I know that there exists an open cover for the union of A and B, and it can be as close or to this mu, the outer measure of A and B, union of A and B, as possible. Right. So what I'm saying is that for any epsilon greater than 0, there will be an open box cover. I call it IK. And for any of this open box cover, just make sure that I will cut it into smaller pieces. For each EK, if diameter is large, I will cut it small until the diameter of the IK is smaller than half of D. Okay, I can always do this. Its D is this distance, it's positive. So the purpose of doing this is I have an open box cover for the union of A and B. The union of A and B. And since the diameter of this IK is smaller than half the D, and the distance between A and B is D, so that means I'll have this like A, this like a B, so this distance D. So if I look at the individual IK, I'll see that since the diameter of the IK is covering is less than half D, so that means it's either intersecting with A or intersecting with B, or somewhere else. But in that case, the IK would not be helpful. I just remove it. But if it's covering one of them, you cannot cover the other one, right? If covering one of them, you cannot cover the other one since the diameter of this is less than half of D. Okay, so in this case, we know that on the one side. So I can partition this IKs into two groups. So one group is only overlaps with A. The other groups only overlaps with B. So we know that since this D is greater than 0, we can partition or split this open box covers into two groups. You can say split this open box into two groups, which we call IK1 and the IK2. So the IK1 will not overlap with the B, will be equal to empty. Okay, and also the second group will not overlap with A. Okay, so I can separate them into these two groups, and then we can see when I take the measure or the volume of this first group, I know that they must be able to cover the A. Right? Similarly, the other group, they must cover the B, right? Because the total, the union of them will cover the union of A and B. So they have to cover A and B themselves. So that means this is bigger than mu star of A plus the mu star of B. Okay, and on the other side, we chose this open box cover not only that the diameter of them are less than half D, but also I want them to be close to the mu star of A union B. So also the union sum of this mu of I k will be less than mu star of A plus A union B plus epsilon. Okay, so we chose this open box cover such that they are close to the true outer measure, which is the infimum of the volumes. Okay, so that means on the one hand it is greater than this, but on the other hand, this is also equal to the sum of the IK, okay, from 1 to infinity, and this is less than the mu star of the union of A and B plus epsilon. Okay, and that's, since this epsilon is arbitrary, we know that the mu star of A union B is greater than or equal to the mu star of A and the mu star of B. Okay, so that's the claim I just made. So what I'm trying to say here is that if the A and B are separated so that the distance is positive, then you can feel free to split their measures. The measure of their union is just equal to the sum of their measures. And you can have finite many ABs if their distance are between any two is positive. Then you can have something similar. The sum, the outer measure of the union will be equal to the sum of their individual outer measures. Okay, and then we're going to use that here. As you can see that I have the union of these D2Js, and J is from 1 to K. That means I have the D2, D4, D6. so on and so forth, and their distance are positive, right? As we showed earlier. This is the EK, say this is the E2, okay, and then we have the E3, E4, and by that what it means that the D2 will be only this part. So they have a positive distance from the previous decay. Okay, so it's like the rings. I have this, and the next one will be this. And then the next one will be a larger ring. But between the rings, there will be some gap. And that's why their distances are all positive. So that's why I can split the outer measure of the union into the sum of their outer measures. Okay, that's how this equality holds because of the claim I just made. Okay, and then once we have this, we can see that on the one side, this is bounded by this. Okay. Oh, by the way, we can always assume that mu star of E is finite. Otherwise, we can just keep growing, and the EK will the limit of the outer measure of EK will also be infinity. That will, in that case, the conclusion will hold anyway. So we only concern the case where this is finite. Okay. And then what I have shown so far is that this says. This is if you look at it or treat it as a series, then the partial sum is always bounded by a finite number. So that means when we tend k to infinity, this will be a bounded in a series, right? The limit will exist, right? So that means the star equation implies that this limit or this series exists, and from this we know that for any epsilon greater than 0, there exists, say, k large enough such that the j from k to infinity of mu star of d2j will be less than epsilon, or less than half epsilon. And similarly, we have shown this is true for the even numbered DJs. So we have this as D2, D2, D4, right? And we can also take this side when we reach to here. So I will take this, this quantity will be bigger than or equal to the union of the D2J minus 1. So that means the union of D1, D3, D5, and we have something similar to this. And that also means that the series here will be bounded above. So that means it is a finite, the series has a limit. And by that, we know that the tail can be arbitrarily small. Okay, so that also means that I can get J mu star of D2J minus 1, and it's also less than this, okay, for k large enough. And now you can see we have this mu star of E, and we know that is the mu star of the union of everyone, as is from 1 to infinity of EK. We know that this E is just equal to the union. And now let's split this union into 3 pieces. One piece is everything less than or equal to 2k. So the k is the one we found here. Okay, so capital K here. So I will split them into 2k minus 1. And then I'll have 2k, 2k plus 2, 2k plus 4. Those even numbered ones. So I have this j from capital K to infinity of I'll have this just 2k of this d 2j, and I also have this j from capital K to infinity of d to j minus 1, 2k plus 1. This will be 2j plus 2, say. Okay, or I can replace this capital K by k plus 1, either way. But anyway, I can split them into these 3 groups. Right, this is my union of ek, and this e2k is just union of the first 2k of those ek. So I should write this. Just the union of j from 1 to 2k of ej. Okay, remember the ej's are increasing, so the union of them is actually just the e2k. So this thing is nothing but just the e2k we showed earlier. So it doesn't matter if we write this way. Okay, so right now, because of the property of outer measures, this is less than equal to mu star of e2k, and plus the outer measure of this, and then the outer measure of the last one. Okay, and we show that this part is less than half epsilon. This part is also less than half epsilon. So the whole thing will be less than mu star of e2k minus plus epsilon. Okay, so what we showed so far is that the mu star of E is less than or equal to this. But now we have showed that the outer measure of E is less than or equal to the outer measure of E2k plus epsilon. And recall that this EK is non-decreasing, it's a monotone, it's non-decreasing. So that's why this one here is less than or equal to the mu star, the limit of mu star E2k. Okay, but the mu star of E2k has the same limit as the mu star of EK. That's why this is less than or equal to the limit of k going to infinity of mu star EK plus epsilon. Okay, and now we have shown that this mu star of E, the outer measure of E, is less than or equal to the limit of the mu star of EK. And because this epsilon is arbitrary, we know that the outer measure of E is less than or equal to the limit itself. Okay, so this is how we show this inequality. And previously we have showed that the mu star is greater than this limit. So we showed the other one here. So that's why these two are actually equal. Okay. So this theorem can be used to prove a very important result we're going to show next, which is that all the closed sets are actually measurable. Okay. So here is a claim. Suppose we have a closed set, then it is measurable. Okay, all the closed sets are measurable. So recall that the goal to show in order to show that the f is measurable, we need to use the definition for any test set T. Recall that the mu star of T, and T can be decomposed into two parts. It can be separated by f, right? One part is the intersection of f, the other part is the intersection with f complement. So if you can show that this is greater than or equal to the outer measure of this plus the outer measure of this, then we're done. Right? This is what we know. So now let me mark this equality as a star. Then I'm going to do the same thing as the previous theorem. I'm going to consider the subset of this. So recall that if I draw the picture, this is T, this is F. So the T intersection of T and F will be this part, right? And the intersection of T and F complement will be this shaded area. So I'm treating this shaded area. I'm going to make a subset of this and let it grow. Okay, so this is a subset I'm going to define. The Fk is a subset of the shaded area. So it's the collection of points such that the distance between the point x and f is bigger than 1 over k. So that means I'm choosing a smaller subset of this so that the points have distance to f bigger than 1 over k. So this is apparently a subset of this. And their distance, the points I'm going to choose here, they all have this positive distance, 1 over k from the set f. So first of all, this is a subset, right? So fk I'm choosing here is a subset. And as you know, I'm going to just gradually increase the k. So this fk will be inflated. And eventually we know that the outer measure of this fk will gradually increase to the outer measure of this shaded area. Right, that's what the theorem proved earlier. And this set is increasing. Apparently, when we increase the k, this 1 over k will be decreased. So it's increasing, and the union of this fk eventually will become the shaded area. Okay, so we're going to use this too, mostly below. Okay, so once we have this gradually increasing or inflated fk, we can see that the fk is a subset of that, right? So that's why when I continue with the star, I can see that this outer measure is bigger than or equal to the same one with this replaced by fk, since fk is just a subset of that. So that's why I have this bigger than or equal to this union of the intersection of f and t and this fk. Okay, as I said, the reason is because this is a subset of that. And moreover, this fk, as we said, is defined as the points with the positive distance to f. So this is a subset of f. Intersection of t and f is a subset of f. And fk, the points in fk has a positive distance from that. So the distance between these two is also positive. So that's why we can split their outer measures. So the outer measure of their union, since these two sets have a positive distance, so we can split them into these two parts. Okay, now following this limit, by applying the limit, we know this is approaching to this set. That's why this is going to increase. The outer measure here will be eventually become this. Okay, so that's why we can just apply the limits on both sides. And then let's say the left-hand side doesn't depend on k, so it just stays the same. This stays the same, but this one grows to this. Okay, so that's why we have this is greater than or equal to this plus the limit of this, which is this set. This measure here. So that's the inequality we get here. Okay, and as we mentioned before, this if this inequality holds, that means the f is measurable. Okay, so this is the very, as you can see, this result is important that we have defined measurable space, but at least we want to show that some basic sets that we saw in Rn are measurable. So here is evidence that all the closed sets they're measurable. Okay, and if they are measurable, then all the open sets will be measurable as well, because the open sets are just the complement of closed sets. Okay, so we can immediately say that the open sets are measurable. And from the open set that are measurable, we can claim that the Borel set is just a subset of the set of measurable sets. Okay, the reason is this Borel set is the smallest sigma algebra generated by those open sets. Right? So it's the smallest, if you consider the set of open sets, then this BRN is the sigma algebra generated by that set. And that is the smallest sigma algebra. And since all these sets are included in the Lebesgue measure, or the set of Lebesgue measurable sets, so that's why, and this M is also sigma algebra, so that's why this is the smallest algebra generated by the open set, and this must be contained in the family of Lebesgue measurable sets. Okay, so now you can see the Borel set is just a kind of special case for measurable sets. Okay, and there are also some sets that are not Borel measurable, but still measurable. For example, the contour set is one of this example. Okay, so next, let's show that suppose we have a measurable set, then we can make I can use an open set to enclose it. Okay, and the difference between this measurable set, and the open set can be arbitrarily small. Okay, so formally speaking, suppose we're given any open measurable set E, then for any epsilon greater than 0, we can find some open set G, so that this G will include or contain this E, but it doesn't contain much more than E itself, in the sense that the measure of the difference between G and E, this is just everything in G, not in E. So suppose this is the E, and we're just making a very tiny, very tight enclosure of E using G. So this inside one is E, and the outside one is G. Okay, we can use a simple open set to enclose it, but the difference of them will have a measure less than epsilon. Okay, similarly, if I have a set E, you can use a very tight closed set F inside E, such that the difference between these two has a measure less than epsilon. Okay, so this is the next second statement. For the same E, you can also find a closed set F, such that F is included in E, but the difference of them has a measure less than epsilon. Okay, so we just need to prove one of them. The other one is straightforward. Okay, so first let's assume the set E has a finite measure. Okay, so if it has a finite measure, that means I can find open box cover for this E with the epsilon as the error. So that means, remember that this one here is just the mu star of E. It's measurable, so the outer measure and measure are the same. And this is defined as infimum of the area of the open covers, right? Open box covers. So this means E is inside the union of K. Okay, so because this is infimum, I know that I can find a specific open box cover such that the area of this, which is this one, so I'm using the outer measure here, but this is just the volume of this open box. So I can find a specific one such that it's not too far from the infimum, meaning that this is just less than the measure of E plus some epsilon. Okay, and on this side, I know that its measure must be bigger than or equal to the mu of E, but I'm only concerned about the right-hand side right now. Okay, so this open box cover, I can take the union of them, and taking the union of them will give me the G, which is still open. The reason is that each one of them is open, and taking the union of them is still open. And apparently, it's since it's open box cover of E, so the G will contain E, right? It will contain E. So the G is open and it contains E. And let's look at the difference of them. The difference of them has a measure. So remember that the G is open, E is which means that G is measurable, and the E is measurable. So the difference of them is measurable. So the measure of this G minus E is equal to the measure of G minus the measure of E. The reason is that E is included in G. Okay, that's why we have this additivity. We know that the mu G is equal to the mu of E plus the mu of G minus E. Okay, because the E is a subset of G, and also the additivity of measures. This is something that the auto measure doesn't have, right? Even if you know that you can decompose a set into two disjoint sets, the union of the two sets may not have the same measure as the sum of the two individual measures. Okay, but for measurable sets, we do have this property. So that's why we have this, and then we move this to the left. We'll get this equality. Okay, so that's how we get this. And now recall that G is just the union of that. So that means by the sub-additivity of the measures, because right now we don't know if this IKs will overlap or not. But at least we know that since the G is a union of the IKs, so I can pull out the union, become the sum. Sorry, it's still the union. I'm writing this as union. So the G is the union of this minus mu of E, but this union I can pull this union outside. It'll become the summation, but I have the less than equal to here. Since this IKs may overlap and less than that. But no matter what, we said that this will be very close to the true outer measure or measure of E. So as we said, the difference between these two is less than epsilon. So that's why I make a difference of them is less than epsilon. All right. So now what we have shown is that we got this G, which is just the union of the open box cover, and we show that it is open, and the measure of this difference is less than epsilon. Okay. So this is the case where the mu E is originally the E is originally bounded. If it's unbounded, if the measure is equal to infinity, then we can decompose this into a countable union of this countable union of sets, so that they make up this E. Okay, so the way is pretty similar to what we have done before. We consider EK, which is just the intersection of E and this ball, B0K. So this ball centered at 0 or origin with the radius K. So it's when K gets larger and larger, this ball is getting bigger and bigger. Okay, I take the intersection of these two, I get dk. Okay, and now I know that this EK will have a finite measure because it's just a subset of a bounded ball. So the measure of this is finite. And because of that, we can use what we just proved here. If it's finite, then we can find, for any epsilon, we can find a G so that the difference between them is less than epsilon. So I'm going to apply the same thing to this EK. For each EK, I'm going to get a open set GK so that it includes the EK, and the difference of them has a measure less than this difference. I'm going to let this measure less than epsilon over 2 to the K. Okay, so for K larger and larger, I want this this GK to be tighter and tighter enclosure for the EK. Okay, and now the GK is defined in this way for each integer or for each natural number K. And now I'm going to take the union of this GKs, and again this G is the union of this GKs, which I call it G, is open because every one of them is open. And then let's look at the measure of the difference between G and E. Okay, so first of all, apparently this G will cover the entire E, right? Because GK covers this. The union of GK will cover the union of EK, which is E, right? The union of EK, and that is E. So that's how I'm going to do here. So the G will contain E, and the difference has a measure equal to, we call that G is defined as the union of these GKs. So that's why I just replaced the G by this. And recall that I can just the difference between this side and the E is just taking the difference of GK and the E and then take the union. So this can be obtained by seeing that this is just the intersection of E complement, right? Then I can use the distribution law and I will put the intersection of E complement with each GK. And then outside I will take the union for K. But inside, if I have the GK intersection of GK and the E complement, that is the same as the difference between GK and E. Okay, and now I have this, and according to the subadditivity, this is the union, and I can pull it out. And since I don't know if they overlap, then we'll just put less than or equal to the sum of these measures. Okay, and now this is what I just said. This EK is a subset of the E, right? As you can see, it's a subset of E. So if I take out the E, it will be smaller than taking out. I will get something smaller than taking out the EK. Right? So the EK is a subset of E. So when I take the E out, it will be smaller than that I take out the EK. Then I take out the EK, right? So I have this. And now recall this, the way we define this GK. We make this GK a very tight enclosure of this EK, and so such that this measure is less than epsilon over 2 to the k. So that's why this whole thing is less than or equal to epsilon over 2 to the k. And now you can see why I put this 2 to the k below, because I need to take the sum over all the k's and still want this to be just 1. So I can put this as when I take the sum of this over the k's, I'll get just epsilon. So now you can see for this unbounded set E, we can still have a open set G such that it includes the set E and also the difference has a measure less than epsilon. Okay, so that's how we proved this statement up to this point. Okay, so I proved the theorem up to this point. Okay, for the other one, it will be just similar. For the closed set, if we have the set E, and then we know that the E complement will be also measurable, right? And since E complement is measurable, we can find some open set G such that it includes the E complement, right? This is what we showed earlier. Doesn't matter if this one has a finite measure or not. We have showed that there will be some open set G such that it includes this, and the difference between the two has a measure less than epsilon. And now we can just define my closed set F to be the E complement. Then the G is open means that F is closed. So F is closed, and I can take a look at the difference of E and F. So first of all, because this G includes the F E complement, so if I apply the complement on both sides, I'll get this. I'll get the G complement included in E, right? I will switch this when I take the complement. And as I defined, this G complement is defined to be the F, or this F is defined as the G complement. Then I know that this F will be included in E. Okay, and also the difference between E and F, or E minus F, has a measure equal to, so we said this the E minus F is just the E intersection of E and F complement, right? And this is equal to, this E can be written as the E complement then complement, right? Double complement, that would be the E itself, and this F complement is just the G. Okay, and then this becomes the G taking intersection of G and the complement of this, and that's just the G minus this. So just the G minus E complement. So the way we chose this this G, we make it open set, and it's a very tight enclosure of E complement, so that the distance less than, or the measure of their difference is less than epsilon. That's why we just follow how we constructed G, this is less than epsilon. So now we constructed a set F that is closed, and F is included in E, and the measure of the difference between E and F is less than epsilon. So that's how we proved the second statement. Okay, just applying the one we just got. Okay, next we're going to show that for any measurable set, we can find a G delta set H. So for any measurable set E, you can find a G delta set H such that the H includes E, and the difference, their difference has a measure 0. And similarly, we can find a F sigma set K such that K is included in E, and the measure of their difference is equal to 0. So it's like you have E here, but you can find a G delta set which bounds it or encloses E very tightly, so that the measure is 0. Similarly, you can use the K to be included in E, and the K is inflated so large that is the measure of the difference is also equal to 0. Okay, so we just need to show one of them. The other one is similar. Okay, so as we showed earlier, for each k, for each integer k, or for each natural number k, we can find a gk, so that the gk includes the e, and the measure of the difference is less than or k. Okay, and then we can take the intersection of these gk's. So the intersection of this open set gk gives me this g delta set h, and apparently since the e is in every gk, so the e will be inside the intersection, which is this h. So e is included in h, and the difference of them is less than or equal to the difference of gk minus e. The reason is h is a subset of gk, okay, as we showed here. So this is less than or equal to the measure of gk minus e, and that is how we chose this gk. We made this gk such that this measure is less than 1 over k. And now you can see that for every k, this set has a measure less than 1 over k. So we know that the measure of this must be 0. It should be measure of this should be 0. Okay. So actually, we can have something similar for non-measurable set, but the conclusion is a slight difference. So the setup is this: we have a set E not necessarily measurable. So in this case, we can still find a G delta set such that this G delta set H will include E, but and also it has the same measure as the outer measure of E. Okay, the measure of H has the same measure as the outer measure E. So here we only have outer measure because the E is not necessarily measurable, and the difference between this one and this one is this. So here we know that this H, the difference between these two is equal to 0. Here we can only get this. We cannot show something like this one, because although the H and the E have the same measure, and the H includes the E, but because the outer measure does not have this additivity, so the difference of H, H and E, or H minus E, is not necessarily having an outer measure 0, okay, because the outer measure doesn't have this additivity. Okay, so but we can get this. So this means that we can find a measurable set, which is the G delta set H here, that includes H, but it's so tight such that the measure is just equal to the outer measure of E. Okay, and the proof of here will be slightly different. And for each natural number k, let's say that the ijk for j from 1 to infinity is open box cover for E, such that the open box cover for E is pretty tight. The sum of their volumes is less than the outer measure of E plus 1k. And we know we can do this because the outer measure of E is the infimum of this kind of things. So for any 1 over k, which is positive, we can find such a open box cover such that this is less than the infimum plus a small positive number. Okay, and then I'm going to define my gk to be the union of this open box and that is open. And then I know that the measure of this GK is less than or equal to the measure of the volumes of these boxes. I don't have the less than or equal to because I don't know if the open box overlap or not. But I know that it's less than or equal to this. And according to our choice of the open box cover, this is less than the outer measure of E plus 1 over K. And now I can take the intersection of this open sets. I call it H. So this H is G delta set. And recall that the GK includes the E. Each GK includes the E. So E is inside the GK. And the taking intersection, the E will be still a subset of H. And also the because of that, the measure, outer measure of E will be less than or equal to the outer measure of H, but the H is measurable, so the outer measure of H is just equal to the measure of H. And on the other hand, I know that H is a subset of GK, so the measure of this is less than or equal to the measure of GK, but the measure of GK is shown to be bounded by the outer measure of E plus 1 over K, so I know that this is just bounded by that. So I know this is less than or equal to this, and that's less than this. That's why I got this bound here. Okay, and now again, as you can see, when we make this K tending to infinity, then we'll see that this mu H just has the same outer measure as E. Okay, that's why we get this. Okay, next we show a similar corollary as we showed before. If we have a sequence of sets, and there's no other requirement. Previously, we required that all the EKs are measurable. Then we have the measure of the lower limit. It's less than or equal to the lower limit of the measures. But now we don't really require those. We don't really have to require those EKs to be measurable. Actually, any set would be fine. And then we can show that the outer measure of the lower limit is less than or equal to the lower limit of the outer measures. Okay, and the proof of this is just based on by using the previous theorem, because for each of this EK, we know there exists a G delta set, we call it the HK, such that this HK contains EK. At the same time, the HK has the same measure as the outer measure of EK. And in this case, we can see that since EK is contained in HK, so the outer measure of the lim inf, so the lim inf itself will be contained in the lim inf, the lower limit of HK. Right? This needs to be contained in the lim inf of HK. The reason is EK is contained in each corresponding HK. So that's why the lim inf is also contained. So that's why the outer measure of this must be less than or equal to the outer measure of this. But the HK itself is measurable, so lim inf is also measurable. So the outer measure of this set is just the measure of it. That's why I have this first inequality. And then using the corollary we showed before, this is less than or equal to the outer measure, the lim inf of the measure of HK. Right? This is for the measurable case. For the sets to be measurable, we have this. And then, because each mu of HK is the same as the mu star of EK, it's the same as the outer measure of EK, so that's why these two are actually the same, because each individual term are actually the same. That's why I have this. So that's how we show this one. Okay, so even for general sets, we can show this result. Okay, finally in this chapter, let's show a very famous, useful example for sets. It's called a control set. So the control set is defined in this way. So we start with a interval 0 to 1 over the real line. So this is just the 0, 1 as the first C0. And then we take out the middle third. So the middle third, we remove it, only the open part. So we still keep this 1/3 here and 2/3 here. So that's how we get the next set, C1. So it's just the interval here and this. So that means this is just a 0 to 1/3 union with 2/3 and a 1. Okay, and the next, for each of these two, I will also remove the middle third. I will have this 4 closed intervals. Okay, that's my C2. So you just can keep going, keep doing this. The next time you will just be removing this middle third, this middle third, also this middle third, this middle third. Okay, so now you can see for each of this CK I showed, K is what happens after the case step. Each one of them is closed, right? It's just a union of finite many closed sets is still closed, and they are bounded because they are always bounded between 0 and 1. So it's closed and bounded. That means it's compact. That's what we showed before. For in Euclidean space, this is the equivalent to saying that this set is compact, and each one of them is non-empty, right? No matter when you stop, you always have some points left. And as you can see, the CK is decreasing because every time you remove something. So I have a sequence of decreasing compact sets, and each of them is non-empty. So that means the intersection of them, or the limit of them, is also non-empty. And this intersection of them, the limit of them, is called the control set. Okay, so bottom line is that the control set is constructed as the intersection of this, or the limit of these sets. And I know that the C is compact, and also it's compact and it's non-empty. Okay, it's compact and non-empty. Several interesting results we can show about this set is, let's see that what's the length of this C, or what's the cardinality of this C. So the C has everything left after we do this procedure, right? So every time you can see we remove something. So first time we remove this middle third. So that's the length we removed out of this. And the second time we removed this middle third. So the first time is 1/3. Second time is 2 of this 1/9, right? And the next time it will be 4/327. So the first time we removed 1/3, second time we removed this, third time we removed this. So if we consider the sum of those lengths that we removed, we see that this is just the sum. This is the infinite sum, and that's just this. And then by easy computation, you can see this is a geometric series, and then you can get the sum of them, which is equal to 1. So that means in total we removed the intervals with total sum equal to 1, and that's how we end up with this control set. So that means the control set itself only has a cardinality 0. Okay, the length of this C is just 0. Okay, so it is a measure 0 set. Surprisingly, it's a measure 0 set and also, although it's measure 0, but we can show that we will only end up with some discrete points, and these points are actually this. So it can be written as a series where this each term is ak over 3 to the power k, and this ak is either 0 or 2. Okay, so we can show this. So I'm not show the details here, but you can just interpret that it can be written in this way. So this is a lot similar to the set of real numbers between 0 and 1 we showed earlier. We showed that for every real number we can try to show it as a sum of ak over 2 to the k. K is from 1 to infinity, and this ak is either 0 and 1. Remember that? So in that case, we show that we'll fill in the entire interval 0 to 1. And now we have something similar like this. Then again, this is binary. It's either 0 or 2. Okay, and this will fill in this will have a cardinality same as the cardinality of 0 to 1, the interval 0 to 1. And that means this C has the same cardinality as 0, 1. And this means that the cardinality of C is LF1, which is the same as the cardinality of the R. Okay, so this is unlike what we saw earlier. Although this one is uncountable, apparently you can see this is corresponding to has a cardinality n1. This is uncountable, but it's measure 0. Previously, we see the set of the rational numbers. They also have a measure 0 because they're just the union of countably many points, and each of those points has a measure 0. So they take the union is still measure 0. But this is a countable set, and it has a measure 0. Here we have an uncountable set, but it also has a measure 0. Okay, so these are the most two interesting properties. So the cardinality of C is n1, but the measure of C is actually equal to 0. Okay, so it's a measurable set. Apparently, as you can see, the measure is equal to 0, so it has to be countable. Or you can see this by taking a look at by seeing that this is actually the intersection of this C case, but the C case is measurable. Okay, so the measure of C is 0, but the cardinality of the C is actually uncountable. It's n1, RF1. Okay, and there are some other properties like the C is nowhere dense. That means the reason is no matter how you look at the 2 points between 2 points, you will take out something, right? So you will always take out something eventually. So you cannot see anywhere that has connected interval, because once you have an interval, for k large enough, it will take out some part. Okay, that make this disconnected, and there will be it has no isolated points either, because again, if you have one point belongs to C, and then within its neighborhood, it must have you take out some parts from this neighborhood, and that means that for any point when you draw a neighborhood, you eventually will take out something, and that means this neighborhood will not be inside the entire C anymore. So that means this point must be it will not be isolated, right? Because there will be ending point, end point that is arbitrarily close to it. So if I have a point like this, you will take out some, you take out some. There will be always ending point as close as possible to this point. Okay, so this is some other facts that are associated with the contour set, but they're not as important as these two. So we show that by this construction, the contour set actually has a measure 0, but the cardinality is out of 1.